In our typical power system, we have generators, including their step-up transformers, buses, transformers, transmission lines, sub-transmission lines, distribution lines, and utilization equipment such as motors and static loads. Also, on most systems, capacitor banks and reactor banks are installed. Now, all of this equipment needs to be protected, but the type of protection used is generally different for each area. So it is convenient to apply the protection to distinct zones. For example, let's start at the generator zone, which includes its associated step-up transformer. Any fault within this zone would result in tripping of the main generator breaker here, and hence isolation from the power system. This will protect against faults in 1, the generator itself, 2, the primary of the transformer, 3, the secondary of the transformer, and 4, the breaker. The next area of protection is the bus zone. The bus will normally have several incoming and outgoing connections. After all, that is the purpose of the bus. Any fault on the bus requires that all breakers, incoming and outgoing, must be opened. So typically the bus zone area will overlap the generator area like this. You can see that these generator breakers will operate either for a fault within the generator zone or a fault in the bus zone. The next area in this particular power system is the transmission line zone, and once again, this overlaps the bus zone at either end. Hence, these breakers will open for a line fault and also for a fault on its respective bus. In this particular substation, we have a transformer which reduces voltage down to distribution level and feeds the distribution bus. So we have a transformer protection zone, and this overlaps the bus zone on either side. On many systems, a sub-transmission line zone would be installed between the transmission and distribution systems. In this example, the distribution line feeds a particular industrial customer who has installed large motor loads. So we have further zones of protection. Here is the distribution line zone overlapping the distribution bus zone, and at the other end overlapping the motor protection zone. Now remember, we're not talking about the type of protective relays installed, only the zones of protection. In each zone, primary protection is installed to protect the equipment within that zone. In addition to this, backup protection is provided from other relays or from duplicate relays. It is no coincidence that as we go through this video training program, we'll be looking at each of these zones in great detail, studying the types of relays, protective schemes, and configurations employed in current practice. Looking at the list of videotapes, you will see generator protection, transformer, reactor, and capacitor protection, bus protection, motor protection, line protection, that is, transmission, sub-transmission, and distribution, pilot protection, system stability, including reclosing and load shedding. But before we get into that, we'll have to study in the first tapes some of the basic technology and fundamentals to help us understand what happens to the power system under fault conditions. Up to now, we've been talking about protective relays. In fact, the whole thrust of this video program is in the application of protective relays. The most common types of relays used for protection are over-voltage relays, under-voltage relays, over-current relays, directional relays, distance relays, differential relays, and I'm sure you can think of many others. We'll be talking about these types of relays in the next videotape and as we proceed on through the series. However, there are other relays installed on the system which do not cause tripping of breakers for protection. But a knowledge of these relays is important in operating and maintaining the power system. One such classification is that of regulating relay. A typical example is the type of relay used to change the taps on a transformer. Another regulating relay is that used to adjust the governor set point on generating equipment and so control the power output. Synchronizing relays are used to check the phase angle before allowing the paralleling of two systems or an incoming generator. Another type of relay is the monitoring relay. An example of this is where the relay is used to monitor the continuity of circuits within breaker trip circuits. Any failure will result in an alarm to the operator. You'll find a large number of auxiliary relays installed on every power system. For example, in protection schemes, auxiliary relays are often used to amplify the action which results from operation of protection relays. For example, supposing this bus differential relay operates due to a fault on the bus. When its contact closes, it will energize an auxiliary relay. This relay, in turn, will close a multiple set of contacts, which will result in tripping all of the breakers connected to that bus. Another type of relay which is extremely familiar to system operators is the reclosing relay. This relay will cause a tripped breaker to reclose after a short time interval, say 30 seconds. But why would we want this to happen? Surely we wish to clear and isolate a fault. Well, the vast majority of faults on overhead lines are due to lightning. The high voltage flashover to ground creates a flow of fault current which trips the breaker on overcurrent or perhaps overvoltage. However, the fault is only temporary in nature and will be removed as soon as the breaker trips. Therefore, when the breaker is reclosed by the reclosing relay, the fault will have disappeared and the line can continue operation as normal. However, if the fault is permanent, for example, perhaps a tree limb has fallen onto the line, then the protection will sense that the fault condition persists and will trip the breaker again. The reclosing relay may be set to lock out at this point, or it may be set to permit one or more attempts at reclosing. Now, don't worry too much about memorizing all of the details. We'll be looking at all of this material in far greater depth in future tapes. One of the problems that concerns operators and relay personnel is how to measure the level of performance of the relays. Will the protection system work properly when needed? Regular maintenance and testing is vital, so as to assure us that the relays will operate when required to do so. But this is not enough. We also need to know how the relays actually performed during incidents of actual fault conditions. After any incident, it is essential that all of the relevant information be recorded and analyzed. This analysis will require good coordination and cooperation between both operations and relay departments. In most utility companies, operation of the protection scheme will be classified as correct only when the following conditions have been met. That is, 1, at least one of the primary relays operated correctly. 2, none of the backup relays operated to trip for the fault. And 3, the faulty area was properly isolated in the time expected. Obviously, knowledge of all conditions on the system at the time of relay operation must be known. This will bring to light, in some cases, incorrect operation of the protection system. This could cause, perhaps, isolation of a no-fault area, or even worse, a failure to isolate the trouble area. The reason for incorrect operation of the protection system could be 1, incorrect setting of relays, 2, failure to change protection scheme to keep pace with changing circuit configurations, that is, inadequate protection. Or 3, failure of some part of the protection system, such as the relays themselves, breakers, CTs or VTs, the station battery, the circuit wiring, and so on. With all of the variables involved, it's often quite difficult to carry out this post-mortem and deduce what actually happened. Fortunately for us, nowadays most power systems have installed data recording equipment, oscillographs and fault indicators that will indicate conditions before and after the fault. These provide valuable assistance in evaluating the actual performance of the protection system. To summarize now, we can say that there are 5 basic factors in application of protective relays. And these are 1, reliability, 2, selectivity, 3, speed of operation, 4, simplicity, and 5, cost. The last 2 items speak for themselves, but let's look a little closer at the others. First, we have to rely upon the relay or relay system operating correctly, that is, to operate and trip out the faulty circuit when it's necessary to do so. The reliability of the relay is tested by inputting current and voltage which simulate fault conditions. The time of operation can be measured in relation to the degree of fault condition. A second aspect of reliability is that the system must not trip out during normal operation. Another important factor of relay performance is selectivity. A relay system is selective when it isolates only the faulty circuit and leaves the rest of the system operating intact. When the relay is correctly set, its selectivity is such that it operates as fast as possible within the primary zone, but it will have a delayed action in the backup zone. This will give time for the primary protection in the external area to operate. This is also known as coordination. The terms high-speed relay and instantaneous relay are often used interchangeably. This means a relay which operates within 50 milliseconds, that is, 3 cycles. But in opening a circuit, we also have to consider the operating time of the circuit breaker. In general, modern circuit breakers operate within 1 to 5 cycles. So we can say that the total clearing time, that is, the relay operation plus the breaker, ranges from about 4 to 8 cycles, that is, 70 to 130 milliseconds. But high-speed relays are not always desirable. Time coordination is often required between protective relays to allow them to operate in the correct sequence. For example, in the primary system, relay operating times may be slowed down to between 0.2 to 1.5 seconds. Now, in this tape, we've presented an overview of the subject of protective relay applications. We've looked at the principles and fundamentals of relay application, as well as the general philosophy involved in operation, in maintenance, and in design of the protective relay systems. This is just the beginning. We'll be getting into much more complicated material in future tapes. For now, switch off the tape and thoroughly go through this material in your workbook.